says an exercise 79 to 90, find the sum. Okay, so we're using our summation notation. I'll try to draw it here. The number at the bottom is the lower limit. So you're going to start when the value equals 1. And we're going to go to the number on the top of the sigma is the upper limit. So in this particular case, without even looking at what's after my sigma, I know that I'm going to sum up the terms from 1 to 5, just based off of this, okay? And then this tells me what's after the sigma actually tells me what I'm actually summing. So in this case, it's 2I plus 1. Okay. So if I want to find the sum without a calculator, what I'm going to do is I'm literally going to evaluate what does this evaluate at when I equals 1 all the way up to 5, and I get the 5 from my top. So I'm going to do 2 times 1 plus 1. Excuse me. So that's going to be my first value. Then I'm going to add 2 times 2 plus 1. I'm going to add 2 times 3 plus 1. 2 times 4 plus 1. And 2 times 5 plus 1. Aiden's probably going to be faster at the math than me. So it's 3 plus 5 plus 7 plus 9 plus 11. So 14 plus 14, 28 plus 7 more is 35. So the sum of those will be 35. If you look at something like number 81, sorry, if you're watching this is from 8.1. It's going back to 8.1. If you're looking at something like number 81, got it. Where we have the sum from k equals 1 to 4 of 10. Okay, so you can see that there is no k value in here. It's just 10. So when k equals 1, it's 10. When k equals 2, it's 10. When k equals 3, it's 10. And when k equals 4, it's 10. And so then we have 40. So that's all you have to do for those. Desmos can evaluate them too, but if they're as simple as that, it's just almost easier to just do the problem than to mess with putting it in Desmos and all that good stuff. Does that make sense, Jennifer? Sure, no problem. Cool. All right. Any other questions? All right. So we're going to dive into 11.2. I think that today should be shorter. Of course, when I say that, it means it's not going to be shorter, right? I really do think today should be a little bit shorter. Okay. Here we go. So if you remember on Monday, we started chapter 11, which is limits. So what we're talking about are functions that obviously if they have a value at a certain limit, then we can easily find the limit. But we're talking about functions where we're looking at the limit of the function as it approaches a value, and it's usually a value that the function can't actually reach. Sometimes it can reach that function, but sometimes it can't. And typically, what we're looking at is functions that what happens when you're trying to reach a limit when it's 0. So what I mean by that is if you look at number 4 here, we have x squared minus 1 over x plus 1. So we know just by looking at this function, and let me make this a little bigger here. That's what I was looking for, control. There we go. So just by looking at this function number 4, you know that if I put in x equals -1, right? -1 plus +1 is 0, and I know in math I can't divide by 0. So if I wanted to know the limit as x approaches -1, I know that I'm going to have an issue just plugging in x equals -1 and finding that limit. So what we learned is that if we want to find the limit, for example, in part C, part A and B are easy, right? The limit as x approaches 1, I can just look right here. When x is 1, my function equals 0, so it's 0. But what happens as x approaches -1? Well, if I really would graph this, there's a hole in my graph right here when x equals -1 because there is not a value for that function at x equals -1. But I can look based on the values that are approaching -1 from both the right and the left. I can look and see that, oh, well, when x equals -1, the limit as x approaches that is -2. Okay, and then we talked about some techniques, how we can use graphs, obviously, to find limits, and then we can use some algebraic techniques to find limits as well. So I think we kind of left off down here in the 6 through 16 area. I know I assigned 1 through 15 odd, and I mentioned that you may or may not, once you get to like, here I have my book right in front of me, I should look. You may or may not know how to factor these higher level quadratics, so you can use graphing if you don't know how to. I did want to go ahead and do number 10, which looks like number, if I can find it in my book here. Dun, dun, dun. Number 10 looks a lot like number 9. So of all of the ways to factor higher order quadratics, I think this is one to kind of review or learn if you have not learned it yet. Try again. I want to send it to Paint. That's what I wanted to do. Okay, so number 10 is a lot like number 9 on your paper. Again, if I want to find the limit as a approaches -4 of this function, what I noticed first off is if I put in -4 for a, I get divide by 0, right? In fact, I get 0 over 0. And so I know that finding the limit for this function isn't going to be as easy as just plugging it in. One of the easier techniques is to graph it, right? Or to graph it and use a table feature. Those are kind of similar, right? And I can figure out what happens as I approach -4. If I wanted to do this algebraically, what we can do is we can actually try to simplify our function, right? And create another function that's similar, but maybe goes over that point at -4. Okay? So what I mean by that is, can we possibly factor a cubed plus 64? So has anybody done anything like that before? I know you've done a ton of work factoring quadratics, right? We spend a lot of time doing that. But has anyone factored cubics before? Yeah, see, it's in there, right? Somewhere. Aiden, I know. I honestly had to look it up again also because you spend a lot of time with quadratics, but then after that, yeah. So I just wanted to do this one. The other ones for 11, 11, 13, and 15, I'm fine with you just using graphing or table features. But I just thought I'd show you how do we factor a cubed plus 64. And what do you notice about just 64 set off any alarm bells for anybody in their brain? So another way that we could write a cubed plus 64 is we could write 64 as 4 to the third power. So this kind of looks like, when you have two squares that you're factoring out, but now we have a cubed and 4 cubed. So again, not something I would expect you to remember, but I thought, oh, it's worth just reminding people that if you have in the general form x cubed plus y cubed, you can rewrite that as x plus y times, I'm going to run out of room here, times x squared minus xy plus y squared. Okay, so these forms match up. So this is pretty much just rewriting a cubed plus 4 cubed as a plus 4, okay, times a squared minus 4a plus 16. So the benefit of rewriting that is that now when I go to take my limit, when I go to what I'm actually trying to do, right? The limit as as a approaches -4, right? Instead of writing a cubed plus 64, I'm going to write a plus 4 over a squared minus 4a plus 16 over a plus 4. And I can cancel out my a plus 4s. Okay, and so now I can actually observe the limit by putting -4 into the quadratic that's left over. So I end up getting -4 squared minus 4 times -4 plus 16. So I end up with 16 plus 16 plus 16, which is 48. So not to totally lose you in the math, but 6, 8, well, I should say 5, 7, and 9, you can definitely factor out to figure out where the limit is. The higher order ones, we don't have to. Just a reminder of how the other methods that we were doing, we can also take this to Desmos, right? Or your graphing calculator. Either one will work. And I have that up here. Start graphing. Maybe. All right, so we can also take it to Desmos and say we have x cubed plus 64 divided by x plus 4. There we go. Make sure I write the equation right. Okay, so again, we can look at our graph, right? And we want to know what happens as x approaches -4. So we're going to pinpoint our graph. Where is -4? And we can scroll around here. You can use your trace feature if you're using your TI. Oh, I did. Okay. Yep. Okay, further up here. Keep going. Keep going. Here we go. So you could use a trace feature. You can see as my number gets closer and closer to -4, I am approaching positive 48. Right? And then if I get to, oh, look it. Desmos actually gave me a little hole when I was clicking there. When I get to -4, it's undefined. And then if I go a little past that, -4.002, I'm at 48.025. So that's how we can verify, okay, my limit as it approaches -4 is 48. Again, you could also change this to a table, and you can put in some values that are really close to -4, but they're not quite there, and also find the limit that way. Okay. So that's just, again, kind of a reminder slash um, update on a little bit more complicated one. All right, so then in 29 through 37, we switch gears a little bit, and it says 29 through 36 and 37 here, use a graphing utility to graph the function and approximate the limit. So in these functions, we actually are just going to go straight to our graphing function. So for example, number 32, the limit as x approaches 9 of 3 minus the square root of x over x minus 9. So again, if I know that, if just visually looking at this, if I put in x equals 9, I'm going to get 0 on the bottom. I'm actually going to get 0 over 0. And so I need to figure out what happens as I get close to 9. So I think these problems are a little easier because they want you to go straight to graphing, right? We're just going to, again, pop in your graphing tool, type in the function, make sure you get the function in right. All right. Get all your, do extra brackets so that we can make sure that we're dividing the right things. I will admit that I think Desmos does a little better job of visually showing you what you're graphing versus with your TI, you just have to be sure that you don't end up, like for example, for this problem, it's really easy when you type in your TI to end up with, instead of divide by x minus 9, it's easy to end up with divide by x minus 9 outside the function. So just make sure that when you're typing it in, especially your TI, it just make sure you put some extra parentheses in there to make sure you're getting your equation right, because that's usually the trickiest part when you have to graph it. Okay, so we want to know what happens as x approaches 9. So first we have to find our function. Okay, so our function's way down here. And we want to scroll in a little bit, and we want to find out what happens as x approaches 9. So visually I can just look here, right? Yes, right at 9, it's undefined. Desmos does actually give me the open circle. So it looks like as I approach 9 from the left and the right, okay, I'm approaching negative 0.166 is what it looks like to me. And it's rounding for me. So if I'm not quite sure, I can also switch to my table, which again, Desmos has a table for you, right? I want to know what happens when I get really, really, really close to 9 on both sides. Okay, so it looks like as I'm approaching 9, my limit of my function is negative 0.166666. Does anybody know what that is as a fraction? One-sixth, right? Or you could put it in decimal form. So, for example, for this, I would say, all right, I should have just done it this way. All right, the limit as x approaches 9 of my function is negative 0.16 repeating, if I can draw with my mouse, or negative 1/6. So those are kind of as easy as that. Okay. So there's a few more that I wanted to show you. Um, and it's the last little bit of your homework in 11 too. So we're going to talk about number 50, 52, 54, and 56. And then on Monday, we'll start 11.3 because I know you guys have tests to work on as well too. So what I want to show you in 51 and 50 or 50 and 52 is that sometimes we look at the limit as it is approaching from one side or the other. Okay. So if you remember, we said that for a limit to exist, right? For a limit to exist, we it has to approach the value from this. Sorry, for a limit to exist at a certain point, the function has to be approaching the same value from both sides. So we did a problem like this on Monday where it was a piecewise function where from one side it was approaching one value, from the other side it was approaching a different value. So that function actually didn't have a limit at that number. So what you'll see here is sometimes in math, we'll actually be asked to find the limit as we approach from a certain side. So it's actually kind of hard to see on here, even though I try to make it bigger. But for example, number 50 says the limit as x approaches 5, and then you'll see a little plus up there, if you can strain your eyes and see. Or the limit, and number 52 says the limit as x approaches 0, and then it has a little negative superscript above the 0. So what that is when we evaluate one-sided limits, okay? So this is, for example, I'm going to take a generic one here instead of talking about these. So if I go into Desmos and I give you the function absolute value of 2x divided by x. Okay, and I look at my function, and I want to know what is the limit as this function approaches 0. Okay, so if I just asked you, what is the limit as this function approaches 0, you would have to look and see, oh, well, as it approaches 0, from the left-hand side, right, the limit would be -2, but from the right-hand side, it's +2. So there actually is not a limit as x approaches 2. Okay. Let me open this up so I can write this down. So if I asked you to find for this function, I'm gonna call this f of x. Okay. So if I say what is the limit as x approaches 0 of f of x, you could say that that does not exist, right? Because when I'm looking from my left-hand side, the limit is -2. And when I'm looking from my right-hand side, the limit is 2. So they don't converge on a common value. So sometimes if mathematicians want to still figure out what the limit is, but they want to look at it from a different perspective, they might ask this. Well, what is the limit as x approaches 0 from the positive side? Basically, as it comes in from the right-hand side. So when you see this positive here, it's asking what is the limit as I approach from my right-hand side to 0? Well, that I can do. So if I have the limit as x approaches 0 coming in from the positive side of f of x, that would be 2. Okay. And if I wanted to know the limit, if I can spell right, the limit as x approaches 0 from the negative side of f of x, then that's looking at the limit as it approaches from the left-hand side, and that is -2. Okay, so that's called a one-sided limit, and sometimes mathematicians will do that because we can't find the limit, right, of the overall function, but if we can find the limits as from each side, then that can give us a better idea about the graph. Okay. Um, okay. So, for example, if we wanted to do number 50, it says, we'll do this quickly. In exercise 50, graphically approximate the limit if it exists by using a graphing utility to graph the function. Numerically approximate the limit. Part B, numerically approximate the limit. And part C, algebraically evaluate the limit. So kind of a good review of all of our different functions, but let's kind of see how this plays out. Okay, so we have 5 minus x, 25 minus x squared. First, we want to graphically approximate the limit. So that's easy, right? We all can type in our calculators. 5 minus x. Oh, left my other function in there. Also, don't do that if you're graphing. 5 minus x over 25 minus x squared. Now I'm just going parenthesis crazy. All right, so we want to know the limit as x approaches 5, and then we have a positive subscript. So we want to know as 5 approaches from the right-hand side. Okay, so if we look here, in this particular function, it actually is approaching the same value. So as x approaches 5, it looks like we are going to have a limit of 0.1. Right? Everybody agree? 5 is undefined, but really close to its 0.1 kind of comes into convergence. So part A, we would say the limit is 0.1. Part B, we're going to use a table function. So again, we're going to get really close to 5, 4.999, 5.001. And it looks like it converges here. We can even add a few extra numbers in here if we want to get really precise, right? As x approaches 5, the limit is 0.1. And then if we wanted to graphically do that, we could. So this one, it actually doesn't matter that it approaches from the left or the right-hand side. What about number 52? Let's look at number 52. So number 52 is the limit as x approaches 0 from the left-hand side of the square root of x plus 2 minus the square root of 2 over x. Okay, so let's see what happens with this guy. Again, this is probably one that you want to make sure that you're typing in your calculator right, getting the square root correct. Make sure you're dividing everything in your equation by x. Oh, well, this one is pretty easy too. I actually did both of these just numerically. I didn't do my graph. So here we go. So as x approaches 0 from the left-hand side, these aren't very exciting ones. It looks like we get close to 0.35. 0.35. We're converging to 0.35. So again, if I go into my table feature, this isn't a very exciting example, sorry guys, as I get closer and closer to 0, 0, 0, 0, 0, 1. A few zeros in there for good measure. Let's just keep, oh. All right, looks like I'm converging on 0.35 as I get really close to 0. Okay. Any questions on that? Those were not very exciting examples. I was actually thinking of my other two examples of 54 and 56 when I was talking about those. Okay. Let's look at number, I was thinking the wrong thing. Let's look at your last homework problem, number 55. Okay. It says graph the function, determine the limit if it exists by evaluating the corresponding one-sided limits. Okay. So number 55 is 1 divided by x squared plus 1. I think this is going to be a little bit more interesting than these two that I just did. In my brain, I was thinking these are the ones, not the ones I just showed you. So, okay. So number 55 is the limit as x approaches 1 of 1 divided by x squared plus 1. So we want to know what happens as x approaches 1. Okay. So here we have it on our graph, right? We want to know what happens as x approaches 1. And so this is actually just a value, which is 0.5. So the kind of anticlimactic, if you look at it from the left, right? If I just looked at this as it approaches from the left, so what is it? 0.49 and 0.51. No, that's not what I'm trying to do. Sorry. I'm thinking in my brain what the limit is. 0.999 and 1.001. You can see that my limit is at 1/2 or 0.5. Okay, then what about number 53? We skip back a little bit. Number 53 is the limit as x approaches 6 of the absolute value of x minus 6 over x minus 6. So again, this is number 53. I have the absolute value of x minus 6 divided by x minus 6. And I want to know what is the limit as x approaches 6. Okay, so what in this exercise it says determine the limit if it exists by evaluating the corresponding one-sided limits. So as x approaches 6 from the left-hand side, the limit is -1, correct? And then as x approaches 6 from the positive side, the limit is +1. So the question is there a limit? Let me pull this up so I can write on it. Oh, it is letting me write on it. Okay. So the question is, does the limit as x approaches 6 of this function exist? And so the answer would be no, that it does not exist because does not exist. Because from the left-hand side and the right-hand side, they're approaching different values. Now, if I asked you what is the limit as x approaches 6 from the negative side, you could tell me, oh, well, that is -1, right? And the limit as x approaches 6 from the positive side of this function, you could tell me, oh, well, that is +1. Okay. Um, I think that is it for today. We will start with 11.3 on Monday. 11.3 is what we actually use limits for. One of the things we use limits for, which is to find the derivative, which is a way of finding the slope of a line at a certain point. So we're going to keep using limits, but we're going to kind of shift gears a little bit how we're going to use it. And that is it. So thank you for coming today, guys. Have a great day. Let me know if you have any questions on the test or anything, and I'll see you on Monday. Bye. Sure. Absolutely. 8, 3, 59 through 72. Let me flip there. Okay, so some more sums, right? Do you have any preferences? Okay, so this one is a little bit different than the other one because this is a infinite geometric series. So we actually have a formula to help us out. So you'll notice in the other ones that we were doing, let's see. Let's pick number 63. Okay, so number 63 says we want to know what is the sum when I start at 1 and I add up to infinity, right? Of 2 times 7/3. Actually, let me do 61 and then I can do 63 just because it has the n minus 1, which is possible to do, but I just want to start with well, yeah. Let's start with 61 and then we can go to 63. I always, all right. So this is 61 now. Okay. So when we have this, they call this the sum of an infinite geometric series. Obviously, it's infinite because we're adding all of the values up to infinity. There's actually a formula that we can use to find this. So the formula is that the sum of a series that goes from 0 to infinity of some constant times our ratio to the I power equals, and then we do our first term over 1 minus r. Okay, so in this particular case, our first term is 5, right? So if I wanted to find the sum of this series, I'm going to do 5 over 1 minus, and then my ratio, right, is -1/2. So it's going to be 5 over 1 plus 1/2. So now it's just a matter if you want to do 5 over 1.5. And then when you multiply that out, you get, my brain is not working. Oops, I even typed in the wrong number. 3.3 repeating. So if I add up all of my terms, I'm going to eventually get to 3.333 repeating. Okay. I think I actually haven't tried this in Desmos, but I would like to try it really fast to see if how Desmos handles it. I don't know if it knows what the infinity is. Let's see. So if I said the sum, not of that. So we'll do from x equals 0 to, let's just put in a gigantic number to simulate infinity of 5 times negative 1/2, again, too many parentheses, to, to the x power. No, to the x power. Oh no, it didn't like it. My equal sign. Oh, here, hold on, let's see. Oh, maybe it doesn't like this. I don't know. Well, Jennifer, I was trying to figure out if I could do it on here. It just feels like I should be able to do it on here. Maybe it wants me to use n. All right, so I'm doing something wrong. But anyway, you can use that basic form to find the sum for any of those problems. So you take the first term, which is what you're multiplying by, and then you divide that by 1 minus the ratio, the common ratio. I don't know if that helped or made it more confusing. Okay, cool. All right, any other questions you want me to go over? All right, great. Have a good weekend, and I will see you guys on Monday. Bye, thanks.